So guys, we are going to continue a discussion with respect to sample variance. And as you all know from my previous video, I had written the formula as S square is equal to, which is also mentioned as sample variance. I is equal to 1 to small n, okay, where n is actually my sample data, right? Where n is actually my sample data. And then we also write x minus x bar whole square. This x bar is nothing but this is my sample mean, right? Sample mean divided by n minus 1. So this is the formula of actually calculating the sample variance. But the question rises that, Krish, if we go and see probably the population variance, if I just go and see the population variance is given by sigma square. I can write summation of I is equal to 1 to capital N, where N is actually a population data, x minus mu whole square. Mu is the population mean divided by capital N. Now here we are dividing by capital N, but why we are dividing by small n minus 1 in this sample variance? Why not n, right? That is the specific question over here. And this entire thing is also called as Basel correction. Okay, so we'll try to understand the reason why we are discussing this, because this is a very important interview question. Okay, I've seen many people getting this particular interview question in their interviews itself. So we're going to just understand why probably we have to divide the sample variance by n minus 1. For right now, let's consider that I'm just using capital N. Okay, so let's consider that I'm using capital N over here, or sorry, small n over here instead of n minus 1. Now, what happens is that, see, whenever we have a specific population data, understand one thing, if you have a specific population data, and suppose if I consider the sample, from this sample, we should be able to make some inferences of this specific population. Now, what kind of inferences we can actually make? The different inferences we can actually make regarding the population mean, regarding the population variance, different thing. We can actually make a lot of inferences, and that is why we actually select sample data and we perform various experiments and we try to make some kind of inferences and conclusions about the population data. Suppose let's consider that I am just going to use the same formula to calculate the sample variance, and for the population variance this is the formula, and then we'll try to understand why we should divide by n minus 1. Let's consider that I have a variable called as ages, right? So I have a variable called as ages. Now probably this is my population data. Let's consider that I have a lot of data over here, and I'll just try to plot it in a specific graph. So let's consider that this is my various ages value like this. And as we go towards the right hand side, the value will keep on increasing, right? So this is my ages, right? Now in this particular scenario, what is actually happening? See, if I try to go and this is my population data. Now it's very much simple. If you go and try to calculate the population mean, I may be getting somewhere here. The population variance will again be somewhere near to this particular value. Everything will be there. Now what if I have a specific scenario wherein, instead of taking the entire population data, now I just randomly select some kind of population sample data. Okay, so let's consider and let's select some kind of sample data over here. So this is my sample data that I am collecting. Okay, this is the sample data that I am collecting. This is the sample data I am collecting, right? Now in this particular scenario, when I collect this kind of sample data, then what will happen? If I go and try to calculate the sample mean, it may be somewhere near to this. It may be somewhere near to this. It can be here and there. But approximately, if you try to see, the sample mean, which is denoted by x bar, may be approximately equal to the population mean, right? Obviously the population mean, and obviously the sample variance can also be approximately equal to the population variance, which is given by sigma square. So these 2 points we can definitely come out from this specific thing. Now what if, okay, this point is very fine because I'm randomly selecting the sample data, I'm computing the mean, I'm computing the variance, and it is approximately near to this population mean and population variance. Now what if there is a scenario, okay, and let me just write down the formula over here of the sample variance, okay, and right now I've told you I is equal to 1 to small n x minus x bar whole square divided by small n. Actually this should be n minus 1. For right now I'm just keeping it as n. Now what if I select some points? Let's consider that I'm selecting some points which will be somewhere here. Let's consider that I'm selecting this 4 points as my sample data. Now when I compute the 4 points of this sample data, then obviously you'll be able to see that I'll be getting the mean over here. Let's consider that this is my sample mean that I'm actually getting. Okay, sample mean. Now if I try to see the distance from here to this population mean, it is obviously very big, very huge. I know I'm not randomly selected the sample right now. I've specifically chosen some sample data. Okay, and now when I'm computing the sample mean, obviously I can see from the population mean it will be very far, and when it is very far, obviously the sample variance will also be very far than the population variance, right? So in this particular scenario, what I can actually consider, or what I can come up with some kind of conclusion, let me use some different color, x bar will be very lesser than the population mean mu, and the s square will also be very lesser than the population variance, right? So this two, we can come up with this kind of calculation, this kind of sample data when we are picking. So why this may be happening, because just understand, because there may be different scenarios that I may pick up data from here, it may be from there, you know. So if I am specifically using this particular formula for this condition, okay, this particular formula for this condition, what I am actually doing is that I am underestimating the true population variance. Okay, the true population variance when I'm using this specific formula, right? Now in this particular scenario, what we do is that instead of just dividing by small n, I will now divide by small n minus 1. Now in this scenario, when compared to n, at least this gap will definitely get reduced, because n minus 1 is a smaller number when compared to n, right? So that is the reason that this entire sample variance is getting divided by n minus 1. And this scenario is just to come up with unbiased estimation. That basically means you are not underestimating the true population variance. Instead, you are focusing on with different sample data. Even though I use n minus 1, it will not underestimate the true population variance, and because of that, the sample mean and variance that we are probably going to compute will be approximately near to, or the gap will be very much near to the population mean. This entire scenario is also called as Bayesian correction. Okay, and as we go ahead, there's also a term that I'm actually going to use, which is called as degree of freedom, DOF. Degree of freedom is usually given by n minus 1, and this usually happens for sample data. Now in this particular scenario, this is my n, this is my sample data, and this usually happens with n minus 1. So this too also you can actually tell to the interviewer. About degree of freedom, we will just try to understand more as we go ahead with respect to this kind of sessions. Okay, so yes, let me continue the next topic, and in the next topic we're just going to revise the entire formula that we have discussed till now.